These days, most of us pay attention to how we live. We recycle, we try to use less water and electricity, we walk or bike or drive more efficient cars. But a lot of us never really think about where we live, or work, or go to school. I mean, a building's a building, right? Not necessarily. Let's say you grow a bunch of plants on top of your building, and they use sunlight and water and carbon dioxide just like they're supposed to. Suddenly, you've decreased your energy bill, reduced air and water pollution, and made things a little greener. Places all over the world have tried it. So why aren't there more green roofs? Well, is it worth the extra work? It makes sense that plants on a roof would keep the building cooler, even if they only provide a little shade. But what's really going on? Where's the heat energy going? How does a green roof change the way a building transfers heat?
So that simple question led us onto a 10-year chase.
Yelena Schrebrich is an architectural engineer at Penn State University who studies energy flow in and around buildings. She and her students built their own green roof, but with their model, they can control the weather to test what really happens when sun, rain, wind, and plants all work together on the roof of a building. But experiments don't always go as planned.
Our first facility was so poorly designed that it caught accidentally on fire and we had to remove it. But it was a great learning experience.
Just because you're a talented engineer doesn't mean you have a green thumb.
Plants do die, they get sick, they need maintenance.
So they went to an expert. Rob Burgage is a horticulturist. He knows all about plants. So Yelena mentioned that they actually killed a lot of different plants when they were trying to figure out what would grow really well on a roof. Can you explain to us a little bit about how you help them choose the right plants for a roof setting?
Okay, so the plants we pick are adapted to growing in a harsh environment. What we're really trying to achieve is something that is more or less in balance.
So you said 50% of the water that would normally have run up is actually taken up by the plants and put back into the atmosphere. How do plants do that?
It's called evapotranspiration, and it's a normal process that all plants go through. They take water up and they release it into the atmosphere.
Evapotranspiration is one reason a green roof keeps a building cooler in the summer. Instead of being absorbed by the building, heat from the sun is transferred to water in the plants and soil and released to the atmosphere. Okay, so we've got a lab. The plants are alive and well. What's next?
One of the major questions we wanted to answer was what's the best way to analyze our data or collect the data for the first place.
So you wanted to recreate some of the conditions that might be outdoors in the lab and then try to measure the different variables?
Right. Well, for part of the experiment, we needed numbers on how many leaves were actually in this entire sample. So that was fun. We had to measure each and every leaf that was in that probably 2.5 inch by 2.5 inch square. It was around 4,000 leaves.
That big?
Yeah, probably. Yeah.
4,000 leaves.
Yeah, so I got my counting skills on that there.
So you take a small space and then use math to calculate about how many leaves are in a much larger area. Beats counting to 1,000,000, I guess.
It's a lot easier to start on a small scale than it is to just go gung-ho at a big project. So if we understand a small scale, the plan is to move it to a bigger scale and just adjust our findings. We're taking measurements. Some sensors take them every second, some take every minute, but we're always monitoring data.
So they take that data, everything they know about that small space, and identify all the factors that affect energy flow. With all these numbers, they can start to figure out how the energy moves within the system. Then another lab member, Paulo Tabares Velasco, uses math to take what they learned from the lab and turn it into a computer model to explain what happened in their experiment and predict what will happen in the real world. So, Paulo, we saw a lot of the different instrumentation you had in the lab and the measurements that you were taking. How did you take the numbers and all the data you got there and make it into a model you might be able to use to predict what was happening outside?
That's something very interesting. We do a statistical analysis of the data, we take average of that data, and then we put it into our model to make sure that our model is predicting the right type of phenomena. In other words, we compare what our model says with the actual data.
So you have to start simple and then make it more complex as you understand the simple parts.
Yes, that's correct.
Everybody knows it's cooler in the shade, but how do you prove it? What's different between a green roof and a regular roof? It may not matter to a lot of people. All they know is that their buildings are cooler and they're saving money. But NSF funds people who want to know more. Engineers like Yelena and Tyler and Paulo, who build models and invent ways to test their ideas. Ideas that future architects and designers can use to make buildings that will change our world for the better. And sometimes the best place to start is at the top.